Yeah. So yeah, if the generators themselves, if suppose you had a set of generators, and there was some subset which commuted amongst themselves, then that is that could be. So I don't remember exactly the definition of the center, but that would be a center. But here J squared, it's actually not part of the generators that generate that group. Okay. You should think of J squared more like, no, yeah, this is, I don't want to say something technically wrong. All right, so shall we move on? Any more questions?
No questions, sir.
Okay.
So what was the Shor's lemma about?
Shor's lemma is saying that if you have an operator A which commutes with all the generators of some algebra, then A must be proportional to the identity operator. That's what Shor's lemma is. And it's pretty important. It doesn't mean that it's going to be the identity operator on all the different representations, but on that particular representation it is. It's a little bit, we'll get to it when we talk about, say, addition of angular momentum, because then we have to deal with subspaces of different angular momentum. Okay, so one thing we found was that the possible values of L. So possible values of L, do you remember what those are?
Half integers.
Yes.
Like
half
Zero,
times
half,
the 0, half 1, 3 by 2, and so on.
2L plus 1.
Half.
1.
Sorry, somebody said 2L plus 1. Is that related to the possible values of L?
Yeah. No.
No, I don't think so.
So what are the possible values of L?
Integer or half integer?
Integer or half integer, positive or negative?
Positive.
Positive. So it's because it's the highest value of M, right? It can be 0, it can be half, it can be 1, it can be 3 halves, it can be 2, it can be 5 halves, it can be, yeah. Okay. And these are, if you had like h bar not equals to 1, then they'll be multiplying h bar. So basically L, what is the physical interpretation of L? And it has the interpretation roughly, I should say, of being the total angular momentum. Okay. So when M is equal to plus L, that means that all the angular momentum, or most of, I should say, or most of the angular momentum is along the z-axis. Okay. It's basically something like this, that it's the angular momentum is pointing along the z-axis. But of course we don't know the x and y value, so we say it is in some cone. We'll talk about the physical interpretation of this in the next lecture in more detail. But roughly, L has the interpretation of being the total angular momentum, and L times L plus 1 is the square. And then given L, we have 2L plus 1 orientation of the Z component of the angular momentum. So this doesn't mean that we know what the exact angular momentum is. And why is that? We know the total, but we don't know what the exact, and we know JZ, but do we know JX and JY?
No. we
Or
don't.
can we know JX and JY?
I think we can, or no.
Maybe what if we defined, ladder operators in terms of J2 and J3, or J3 and J1, and to proceed with the
Yeah, of
same
course.
calculation?
Yeah. But then you would lose the information about JZ, right? Then you would have
Oh,
information.
yes.
Yeah.
Yes.
So suppose we know J squared, it's given by some value of L. And suppose we know what JZ is. Suppose it's some value M. So we have some state LM. So do we know exactly what JX and JY is? Can we find out?
No, I don't think so.
Why?
Oh, we can also think about the Heisenberg uncertainty, maybe.
Yeah, we can't measure them simultaneously.
Why can't we do that?
Because
Why?
they don't commute.
Because they don't commute.
Yeah.
You did a tutorial on this. JX, JY, or JZ in this case, that is not equals to 0. JX, and then similarly, JY and JZ is also not equals to 0. That means that, delta JX and delta JZ is not equal to 0. And delta JY and delta Z is not equals to 0. Right? So, because, if we know JZ exactly, then, we have no information about this or this. Heisenberg, the generalized Heisenberg uncertainty principle. Okay?
Yes, sir.
Okay. So I said that in the last lecture that I would give you a better picture of the ladder. And let me just do that. Just a better drawing, So we have some dot, dot, dot in the middle. And L, and M has L minus 1. And if you apply J plus on it, you get L, M equals to L. And if I apply J plus again, you get 0. But if you apply J minus to this guy, you come back to this one. And then, if you J minus takes you in that direction, J plus in that direction. And if you apply J minus, eventually you come to, L M equal to minus L plus 1. And then another J minus takes you L M equals to minus L. And J plus takes you in the other direction. And if you apply another J minus, then you get 0. And this is the ladder, but this ladder is on its side, whereas here the ladder was, vertical. This is probably a better picture.